So to guide us through this conversation, it is my pleasure to introduce Louis DeBasto. Louis is an award-winning designer and the creative force behind more than 200 yacht builds, ranging from 50 to over 300 feet, developed for many of the world's leading custom and production builders for over the past 4 decades. And to use his words, having this much experience allows him to move beyond conventional design roles and create his own. So with that, please join me in welcoming Luis DeBasto and his exceptional panel of experts.
Thank you, Rebecca. Good afternoon, everyone. We have a really exceptional panel to discuss an issue that is very, very interesting to me, very exciting, and I believe for everyone in this room. We have the group of panelists is here. I'd like each one of you to introduce yourselves. Please start with Sam.
Good afternoon. My name is Sam Wheaton. I'm the co-founder of C-Hub. We provide a maintenance software to the marine industry. We work with data. That's what we do. We're believers in it. And I'm looking forward to talking about a few changes that are taking place in the superyacht marine engineering industry.
AJ Anderson with Wright Maritime Group. Also for this topic, representing an organization, Nuclear Energy Maritime Organization. And we're spearheading some projects, but I'm really here to listen to Derek and Espen because they've got something pretty interesting to show you.
Job, please.
I'm Joep Bollerman. I'm from Lloyd's Register. I'm originally from the Netherlands, hence the funny accent. I'm here to represent the regulatory side of the story and proud to be part of this panel.
Derek.
Good afternoon. I'm Derek Munro, the Director of Divergent Yachting. I've been a captain engineer in the industry for about 20 years. Then I moved ashore to build boats as an owner's representative, involved in 14 builds up to 105 meters. A few Americans, that's about 350 feet. Since 2021, I was engaged by a client to research nuclear in yachting. So it's been a very interesting ride, and hopefully I'll share it with you this afternoon. But basically, it's coming, whether you like it or not, and probably a lot sooner than many think. So it should. Hopefully, we will educate you and change those of you who are on the fence to convince you that it's a lot safer than everyone thinks about. And yeah, we'll see how it goes.
Espen.
Good afternoon. My name is Espen. I'm a naval architect and a yacht designer, and I'll join Derek in showing one possible application for nuclear. I like to say nuclear production as opposed to nuclear propulsion because the propeller is still driven by an electric motor. Anyway, we'll come back and show an interesting concept for what can be done. It's very achievable within the next, I would say, 6-7 years. We'll probably see it. So thank you for having us here.
Let's start with a little bit of history, because when I was growing up, I really was in love with, as a yacht designer, one of the most fascinating boats of the time, which was Savannah, made to propose nuclear propulsions for commercial and cruise ships. And to me, today, that boat still is one of the most beautiful for what it is at the time. It represents really a beautiful dream. It was decommissioned a few years later, so now we are back after the nuclear propulsion was used in military uses and everywhere. So a little bit of that history, I think we should take a look before we dive into the future.
So nuclear power history. I think number one, we have a problem with the word nuclear. If we say nuclear, half of the world is going, oh, this is bad, oh, well, this is terrible, this cannot possibly be good because of the bad history. But the first use of nuclear power was, of course, not a positive one. So either way, once we get up with a better name, we'll use so long we use that. So in 1955, the USS Nautilus, first nuclear-powered submarine was launched. And don't worry, I'm not going to read all those words on the slide because then we'd be here for a while. But just for the people on the back, you probably cannot see all the words there. So I'm just gonna. In 1955, there was the first submarine that was nuclear powered that was brought out, and that was fairly successful. And then there were a couple of other military applications that were following. In 1961, I think she was actually built in 1959. The nuclear ship Savannah that Lou already mentioned. This was a very interesting ship because it was important for the world to see that nuclear can also be good for good purposes. And this is why the NS Savannah came out, and she sailed the world for like 12 years or so as a cargo ship, and actually also with passengers. It was a cruise ship as well. And she was visiting all over the world. There were some places where she was not allowed in, and those places to this day do not allow nuclear ships in port. But either way, so that was a very important step in the history. Then there's a lot of other examples of military applications. Up to 1974, the Soviet Union also joined the group, and then there was a continued investment in the industry, but people started to be concerned about the waste. What are we going to do with all these things? In 2010, actually, we had a very good drive, a lot of interest in the industry to even start building nuclear-powered ships, cruise ships even. And then in 2011, the unfortunate event in Fukushima shut that all down. There was all of a sudden there was a very limited interest in the whole nuclear concept. Up till the 2020s, when the interest was restarted. There's a lot of interest again since the 2020s. I don't know if it's because we finally forgot about Fukushima or because it was COVID and we didn't know what else to do with our time. But in the end of the day, it was good that renewed industry interest had started, and you could see that we're here. And all these things that are all various concept designs, next steps, Lloyd Register getting involved in rewriting the rules, IMO discussions, risk assessments, all these things that are happening since 2020. So there's a lot of activity in this framework. And we expect, as AJ already said, or somebody mentioned, that we will by 2030 or possibly even before that, we will have a ship out there or more running on nuclear power. So this was just to give you that idea. This is the Savannah, like somebody mentioned, a beautiful looking ship. I think she's still around somewhere where people try to preserve her and make it a museum and all that. And this is the future. This is a concept that is Lloyd's Register approved, or we're working with that. And this is a sea transport, I believe it's called. It's a project that is going to operate in the Pacific for transportation and for commercial purposes. So this is incredibly exciting. We are going back to the future from the Savannah time, which was the future at the time. I think even the DeLorean in the Back to the Future movie was powered by nuclear power, if I remember well. So the next part that I've been asked to talk about is the regulatory frameworks. The regulatory frameworks are a little bit complex because it wouldn't be fun if they were not complex, right? I truly believe that most of us would be out of a job if everything would just be simple, but we are trying to make everything work and try to explain everything because it is complicated. And the IMO, the International Maritime Organization, is the organization that works on the regulatory frameworks on ships. That's the industry we're in. So there is actually a chapter in SOLAS. SOLAS is the Convention for Safety of Life at Sea, which has been in place since 1914. Any idea why that was in 1914? Let's make a regulation about how to keep ships safe. Probably had something to do with the Titanic in 1912. But anyway, there's a special chapter in that about nuclear-powered ships. It hasn't been used very much, and it hasn't been updated very much because of the limited interest. At the moment, all that is in chapter 8 on SOLAS has to do with the kind of power plants that have been in place since the 1950s. So all the new technologies are not included in those regulations. And the same thing with safety, security, and safeguards. So there's a lot of work with classification societies and in the IMO to update those rules to also include the newer technologies that are being developed. And I'm sure my esteemed colleagues will go into much more detail on that. So the timeline, yeah, we're hoping 2030 and 2032. So how to get ready for that? How to prepare for that? Because we're building a ship now, and we don't want to be told in 2040, like, well, you can't use your ship anymore because, oh, I really like nuclear power in that, but I cannot do that anymore. So you got to keep in mind that you want to future-proof your ship. So future-proofing your ship for nuclear power, or whatever we're going to call it, that's a challenge because we don't really know what it's going to look like. What we do know that it's probably going to be a black box, much smaller than this room, where the energy is going to come from. And my colleagues here are going to go into much more detail on that. So you have to think about having the possibility to do something with a space on the ship where you can do something with. And there's all kinds of considerations that, again, that will go in there: biological shielding, electric ship arrangement, all these different aspects. But the most important part is that the regulatory frameworks, to the next one, are all going to talk to each other about that and agree. So what you need to do when you're building a ship, you need to, number one, keep an eye on those regulatory discussions. And if you're a NEMO member, which AJ is, and many others are, that you need to participate in those discussions. There is a big conversation or a session in Lloyd's Register office in London in April about the safety aspects of this. Because if you're building a ship, you don't just have to worry about that black box that you have to fit one day, but there's also going to be all kinds of safety features, maybe some extra cables, maybe some extra escape routes, or maybe some extra shielding that you need to consider when you're building a ship, unless you want to rebuild the whole ship. So that's where the nuclear ready part comes from. And then you get to the part where, okay, when everything is done, then we can start operating these ships. So, okay, so operational mission division, you got to be sure that you understand what you want to do. If you're going to stay in a very remote area where it's difficult to fuel, then, you know, nuclear power is a solution for you. Because think about it, you get a nuclear solution on board, you're going to not be fueling anytime soon. You're going to be 10, 15 years without refueling. So all those things, and there's all these different aspects that we can help you with to come up with the best way of dealing with. And of course, the bad part about any of these discussions is the end of life. What are we doing with the waste? What are we doing with the reactor removal and all that? And I'm sure we'll have some good conversations on that. So now I know that I have this, and I've been talking too long already, but I've mentioned all these different things. Focus on the safety parts that are outside the black box, so you can consider this when you're future-proofing your system. Now, I've been talking for like 2 minutes, hopefully, maybe 5. There is a lot of stuff out there on the industry. On our website, Lloyd's Register, we have a fuel for thought section, and there is one of these for every type of fuel. This one is the slide for nuclear. There's a lot of information about there. So much more that I can ever say in a half hour, and much more eloquently put. So I encourage everybody to go and have a look. Is that? I'll give you this one back too. So
Thank you, Joop. All right. Derek, question for you. What is the expected establishment of technology regulation assurance that we're gonna see that? This is for AJ, sorry. Sorry. I'll look at AJ. I messed up the order. Sorry about that. So the question is, when is the expected establishment of technology or regulation assurance to be?
Yeah, so I mean, Derek's been working on this since at least 2020, 2021. And Wright Maritime's been working on it since late 2024. And so we're fresh new on it. But not a lot of people were talking about it. Nobody, even the people that were talking about it, had no idea that it would accelerate as fast as it has between beginning of 25 till mid 26, not even mid 26. It's phenomenal, and it's not. The technology's been there. So the technology's been, in which Derek and I think Espen will also talk about in some detail, maybe me again later on. So when we had a NEMO meeting over several meetings over the last few months, 3 months ago, so that there's technology, it's there. So, and the technology is not the same technology that was on Savannah. It's fission, but it's completely different. And so it's and much safer as Yo just mentioned. And Derek will get into some really great details. So that's there now. And the regulators, which is Yoke and some of the flag states, are already talking about it. In conjunction with IMO, IAEA, they believe that they will have the regulations set by 2030, late 2029, 2030. The insurers, we were in a meeting last month, they said they'll be ready to write insurance for floating ships and floating power plants by 2030. So those are the main technical, operational, and operationally, I think a lot of folks are already working on operation plans. We are, and others. So operationally, we'll be ready in 2030. And of course, as we go operational, we'll continue to refine our operational procedures. So the real thing that is going to be the limiting factor is social trust. It's who's going to let this ship or those ships into their region. And you know, flag states got their responsibility up until the 12-mile limit, and then port state is looking at it very hard and very carefully. So it's going to be social trust, and that's why that Derek spent a bunch of money, flying economy, I think, from the UK. I asked him to come over. So the more that we talk about it, and the more that you guys recognize it, study it, and the more you talk about it, that social trust will rightfully, it's not misselling, it's rightfully will improve, because it's the best future power supply that we'll ever have.
Thank you. So my question now is for Espen. And Espen, as a yacht designer myself, we know we are working on a design for a yacht nuclear propulsion. What can you tell us about the project? Are you designing the yacht around a nuclear reactor, or the nuclear installation fits nicely into your design?
As I said, I like to think of it more as a nuclear energy production on board a basic electric backbone boat, much like a diesel electric boat or ship. And so all the propulsors are driven by electric motors, but electricity is generated by nuclear power. We started off looking at using a given reactor, which is in development at the moment, as an American company called Emerald Nuclear. It has an output of 5 megawatts, and we basically took one of our yachts and looked at how can we possibly implement this. We chose a 120-meter platform with electric backbone, and tried to install 2 of these nuclear reactors. But before I get into the details of that, I just wanted to elaborate a little bit on decarbonizing shipping was a big subject up till very recently. They've been in the background right now with what's going on in the world, but it might come back again as a result of that. But if you look at this graph here, it's very interesting. If we were to go for other alternative fuels, green fuels such as green ammonia, green methanol, green hydrogen, to create electricity from that, they're basically trying to decarbonize the whole fleet of ships today. There just isn't enough energy available to create those fuels. So that is not an option. And that's one of the very good reasons why you would want to go for nuclear power. The three fuel columns you see on the left here represents what it would take, and the three grey columns on the right shows you what has been produced in the EU, in USA, and China, and globally renewables. You can see that it doesn't stack up at all. Nuclear power has a power density which is way, way beyond anything else, and that's why it's so attractive. One of the many reasons why it's so attractive. What you see here and what has changed, some of the things that have changed and makes it possible today is that it uses modular, smaller reactors. As I said, this one here is a 5 megawatt reactor, which is intrinsically safe. One of the reasons why it's safe is because it uses a fuel which is encapsulated. The uranium is enriched to a relatively low level, below 20%, so it's not weapon grade, and it is encapsulated in a material which makes it totally fireproof up to tested to 1,600 degrees and actually beyond. And we still have a pressure vessel, and which protects it from any kind of accidents. And there is a surrounding structure and shielding. And then we have a very safe energy conversion system, but there is no nuclear aspects to that. So this generator here generates a heat, which is then transformed into rotational power through a power conversion system produced by another company here in the States, and that's driving an alternator for producing electricity. One of the interesting aspects of this is the fact that the emergency planning zone, which on the first generation nuclear vessels extended well beyond the size of the ship, and therefore affected the ports, which is one of the reasons why some countries don't allow them into the port, because if there is an emergency, it will affect their ports and their facilities. Here, the emergency planning zone is actually contained within the ship, and that's a big game changer. This diagram here shows how how the energy, the heat is created through the nuclear fission and then goes into the power conversion system, and how the electricity is then fed into the switchboards and battery packs, and you have the various consumers such as a propulsion system, the tail loads, and why not electric tenders. It's a fairly simple setup. It's just the only thing that changes is really the way you produce electricity. This is the vessel we designed, and what's interesting here, the space requirement is very comparable to a regular engine room. The one thing which is different is the shielding, which is here. You can see around the two reactors. The weight of that is about 450 tons, which is still much less than the typical fuel load a 120-meter yacht would have. So weight-wise, you're actually coming out positive. We have arranged for these reactors to be located just below the tender garage. The idea being that you can replace these and have them inspected. Typically, I guess Lloyd's would want to see them, and the manufacturer would like to have a look at them every 5 years. But we have calculated that we can probably have enough fuel for about between 15 to 20 years based on the typical mission profile of the yachts. We have a hatch in the deck in the tender garage. We can remove the shielding elements. They're designed so they can be handled by the telescopic cranes for using for the tender, and we can easily replace that. Just the analogy of a gas bottle in a little sailing boat. You just go in, you take a gas bottle out and it's empty. You get another one and you install it, and that's it. You wait for another few weeks. Here it will be another few years. That's the concept. Yeah, we are working with Emerald, and they're just setting up. Actually, it was created last month, a subsidiary in Norway, together with the Technical University in Ålesund in Norway, where the first reactor will be built, and they hope to have the whole proof of concept up by 2030, and the first shipborne installation in 2031-32 on a commercial vessel. and based on this same system. This is a yacht, which is not for a client. This is a concept we did in our office to show that this can be done. And we are talking to the one client who may be interested in doing this. I think Derek is much farther ahead in that. I'll leave it up to him, but this is over to you, Derek.
Obviously, it's all about safety moving forward. This is the NOx-free. NOx-free is a collaboration that we set up in 2021, which is myself at Yacht Consultancy, Lauren Giles Naval Architects, and Rasmussen Marine. Steve Rasmussen is an ex-Royal Navy nuclear engineer, so and I've known him for a long, long time, and we've always discussed the option and possibility of putting nuclear into yachting. This is obviously AI generated, this graphic, but this is how we believe it'll look inside a large yacht. Now, each one of our units is only 1 megawatt, and you combine it like you would combine a group of generators to build up your power source. Everything is electric, as Espen has said. And we use in our system a low enriched uranium at 5%, which is very, very easily accessible. There's a lot of it. It's easy to make. It's easy to get from global sources. Our unit is modular, so you get the reactor part, which is this section here. And this section is the power generation unit, which uses exactly the same as Espen is using on his, the supercritical CO2 turbines. And it'll create 1 megawatt of electrical power and 2 megawatts of thermal, which, if you don't understand thermal is what we will use to heat swimming pools, hot water for the boat. You can reverse it, use it for air conditioning. Also water, so we can actually make water with this, so you won't need water makers, you won't need a big HVAC unit. So as long as you sit down and plan it in advance, you're going to save a lot of space in the boat. Obviously, the shielding is incredibly important because it's what makes it safe and what makes the public feel a lot better. Very, very similar to Espen's, so I'll skip that one. The unit itself is around about this height, and it's like a big heat exchanger. In actual fact, this week it's arriving in the Idaho National Labs here in the States. In 2 weeks' time, that'll be loaded with fuel, and in 4 weeks' time, we start to go critical. And the reason we're doing that is that your president, Trump, has asked to, there's a small group of people creating these, the 5 megawatt units and smaller, and he's asked that by July the 4th, Independence Day, that someone proves that nuclear is viable in this country. So we believe that we will be the first, if not one of the first, to go critical in time for July the 4th. The 3 S's is shielding, security, and safeguarding. So the shielding obviously is the initial pay packet, and it's 2.8 meters. Our unit is 2.8 meters in diameter, just under 3 meters long. So once you've removed the fuel tanks on the boat and you drop it down to the deck level, the bottom of the hull level, sorry, you start to gain a lot of space inside the vessel. The safeguarding is that all fuel in the future for SMRs and MMRs is going to be tracked. No one can touch it. You cannot service this on board the boat. Engineers will not touch the reactor unit on my unit, Espen's unit, or anyone else's. Once it's in the boat, it stays there, and you can actually put it into a welded box, seal it all off. It doesn't need a lot of ventilation, so you don't have massive ventilation trunks going through your boat like you would from the engine room for your diesel generators. And anyway, it's going to be tracked, it will be safe. And then we have the security, which is obviously how you box it into the boat, how we track it all, how we monitor security around the boat, and that's where Lloyd's and Flag State will get involved, and they'll be making sure we have cameras and we have monitoring and everything else to make the boat secure so that once we cruise in and out of ports, it is safe.
Derek, quick question. 1 megawatt, if I'm not wrong, is about 1400 horsepower.
Yeah, roughly.
So this is scalable.
Yeah.
Okay.
Yeah, definitely. So we've got, and you'll see it in a little bit, we believe that a 40-meter boat will have one of these in it. with a battery bank, an ESS, energy storage system. And the reason we have the energy storage system is that with our system, it'll ramp up and down, can be controlled by the computer, or it'll load follow. So if you happen to be at anchor or you're sitting in a marina and you've loaded right down because you've only got crew on board, if you had to leave in an emergency, you need the batteries so that you can pick up anchor straight away, start doing things straight away while the nuclear package ramps up. And that doesn't take long. It only takes like a minute and a half. But in that time, you want to be moving. So Lloyd's and Flag will want to make sure that we have that safety factor in there. And then on a 60-metre design we're doing, we have 4 units. And on a 112-metre, we have 6. And the design that Joop showed earlier on, which is the future, that has 4 of our units in it. We have approval in principle from Lloyd's for that design, and it is going to be built and delivered, I believe, in 2029, and it will be based in the Pacific for humanitarian relief work. We also have a vessel here in the States, which will have one of these units in it by 2029 as well. So local port authority here has approved that, so we are progressing. So this page here actually kind of explains what happened in Chernobyl, what happened in Fukushima, and 3 Mile Island. So Chernobyl obviously was the Russian, slightly different use of nuclear, badly maintained, bad communications in the system, within the business structure. No one wanted to tell their superiors that they'd made a mistake and they hadn't done their maintenance and everything else. And there was a steam explosion because it got too hot. And I'm just getting into this because we'll show you we don't do that in the future. Fukushima, there was a hydrogen explosion, similar sort of thing. The cooling rams failed, and so things just got too hot. Stainless steel melts at about 1400, 1500 degrees C, and so everything just got too hot for that. The stainless collapsed, and everything went out of hand. 3 Mile Island was actually a meltdown, but actually nothing escaped. There was no radioactive issues. The problem there was obviously they lost billions and billions of income moving forward. So this is actually the design which we have approval in principle from Lloyd's for. So they've decided to put their reactors on the bottom and their power generation above. And you'll note that in this, there is no ventilation, there's no stacks going up the mast. So actually what happens is you've got no decks, you've got no fuel tanks, so you've actually gained loads of storage space. So in effect, the owner gets a lot of space back, and you have a much nicer design. In fact, that'll affect, for the designers, you won't have to go so high. You could potentially have 1 deck less, or whatever, obviously depending on what the client's after. Oops. Well, yeah, that's exactly right. You can put your units at the bow, the back, the middle, wherever it is. And obviously, as Espen said, you want to plan for the future, and actually Joop was implying that as well. So design soft patches. If you're building a boat now and you think you're going to go nuclear, go fully electric drives, azipod shafts, whatever it is you're going to do, and be prepared to move this in. We could, so I was the owner's rep for the sailing of Black Pearl. She has electric drives and diesel. She's diesel electric. If we wanted to, we could take the diesel engines out, put a nuclear unit in, and drive her as well. We're not going to, obviously, because she sails and we don't need this. But it's a possibility for any boat that is currently designed diesel electric. This is actually a different rendering of the same boat. Just to show that we're real. It's an American company. It's called Deployable Energy that we're partnered with. It's obviously just down the road in Texas. We're 100% up and running. We have a gigawatt factory opening at the end of this year. We have another one in planning stages, which will be built next year and the year after. There are 2,500 units already ordered for data centers. We are, apart from deployable energy, I'm personally in discussion with 3 island groups and a few shipyards for powering the shipyards and powering the island. So there's definitely a lot of talk out there at the moment, and we are coming. So our modular reactor is based on similar designs as there were in the Russian design, as there was at Fukushima and 3 Mile. The only difference is we operate at 800 degrees Celsius maximum. At 800 degrees, our system will shut down to 0 if we go above that. So we have no risk of meltdown. We have no risk of hydrogen explosion, mainly because there's nothing in our unit that you can create hydrogen. We use helium as the heat dissipator through the vessel to get to the supercritical turbines. And it's just a totally different, new, modern technology, and I'm not allowed to disclose too much, but we are intrinsically safe, and we are testing in the next 6 months at the Idaho National Lab how safe it is. It'll be pushed to the limits and brought back down again. We may have to adjust our shielding a little bit, but at the moment all the calculations are showing that we don't have to. The guy who started Deployable Energy used to work on oil rigs. He wanted to create something that could power the oil rigs at sea, so it had to be safe. He wanted it to be affordable for everybody. So just like in the old days we had steam, and then we moved into diesel, and we moved to diesel because it became affordable. And so the idea is that we will make this affordable. It's single-digit millions for 1 unit. Calculations are at the moment that you will get your ROI in approximately 3 to 3.5 years. So you can use it for 10 to 25 to 30 years, depending on your use case. So as you can see, it's well worth looking at. It's not just a real big number at the beginning. Our unit, as Espen's will be bought on like a lease term. So the license is held by the manufacturer, not by the owner of the vessel. This makes it easier for you to cruise around the world without having to get licenses for every place you go to. It also means that when we get to the disposal stage, the manufacturer is responsible for the unit, not the ship owner. So the manufacturer will come and take it off the boat, just like this. We believe the changeover could be done in 6 weeks. Cut a hole in the side, take the unit out, slot a new one in, weld it back up again, fill, paint, off you go. The 60% of the fuel is then repurposed. And basically what they do is they take the fuel out and they add a bit more uranium into it, and then that goes into the next unit. The rest of it is taken, it's held in storage, and it'll be used in the future for smaller plants that are already being designed at the moment. So the idea is that there's limited or zero waste. The body of the unit, we estimate at the moment, can be used 5 times. So the heat exchange section I was talking about, the shielding and everything else, all of that should be able to be repurposed and used at least 5 times. So 5 times is what, let's say we've got a 20-year life. There's 100 years of reusing the body on. Yeah, so that's it. That's our unit, and I'm open to any questions. We did sort of say if we can have questions at the end. Is that right? Yeah.
Everyone's got
Hopefully we'll answer a lot of what you're out thinking about now before we finish. And so I'm going to pass you on to Sam.
Some interesting topics there. The main takeaway for me there, maintenance aspect. We've heard that these MMR units are pretty well free. They are concealed. They are on a leasing agreement whereby no ongoing maintenance is required on the reactors by the crew. So that's a major vet. How are we looking? It's a major advantage for the crew. Let's keep in mind, though, that these are going on yachts, and yachts are maintenance-heavy machines, and there are surrounding systems and components that will be maintained. So a quick look at how maintenance is scheduled today. It's a model that not only the marine industry but multiple industries rely upon. It's a model of manufacturers are dictating to us what intervals and what tasks need to be. It's like presidential fake news. The maintenance philosophy we use today is one that's widely accepted. It's the idea that manufacturers dictate to us the set interval that certain things need to happen. And what that allows us to do, and manufacturers to do, is to hedge their warranty commitments based on the assumption that certain maintenance is being done. The limitations with this model are that they don't consider any external factors. They don't consider environmental factors or what's going on outside of their specific component. The other main limitation is there's a general consensus in the engineering industry that we over-service equipment. We're doing too much maintenance, and that in effect has flow-on effects. One of the big shifts that's taking place now is engineers wanting to make data-backed decisions in relation to their maintenance. So they're saying we don't want to do a top-end rebuild just because we have reached an hour's limit. We want to know how the engine's running and then determine whether or not we make that investment and do that procedure. We're in a unique time where we have the old philosophy, the scheduled, the plan-based philosophy overlapping with a new shift in how we approach maintenance. And the new shift is a philosophy that these MMR manufacturers solely rely upon. And it's a philosophy of predictive maintenance that's based on how the equipment is running itself rather than a set interval. It relies upon a network of sensors pulling data in real time and that being shared and the data being processed real time. AI is going to play a really important role in this rollout and how effective these models become. And as we've heard earlier about AI, these models only become smarter with time. So what we'll start to see is yachts that are using these MMR reactors, and it's around the corner, it's 2030 is not far. We'll see that the data that is being captured on those vessels is shared amongst similar vessels so that can shape future decisions as it pertains to the maintenance that's being done. The fundamental shift is away from servicing everything on an interval to servicing what needs to be done when it needs to be done. The predictive model is very much sensor heavy. So one of the main drivers in this shift away from scheduled maintenance is the advancements in connectivity. The introduction of systems such as Starlink has completely sped up the whole process of looking at predictive maintenance. It wasn't that long ago the idea of streaming a game of football or an owner hosting a conference call on a yacht was completely outside of the realm of possibility. Now we're looking at scenarios where real-time data can be pulled from not only engines, but bilge pumps, seawater pumps, hydraulic power packs. All this information can be channeled and brought into a single database where decisions can be made. The maintenance then becomes a process of notification. So the way that this will work is an engineer will receive a notice or a notification saying that a detection of something outside of what it considers normal has been picked up. So an easy example to understand is a seawater pump. A flow rate has been recorded outside of an acceptable range. In addition to that, it could be vibration of a shaft within a pump. If it detects the vibration is outside an acceptable limit, then it would prompt the engineer or the maintenance manager to consider a certain course of action. Now, an important part of this entire ecosystem is documenting the route to resolution. So not only is the system notifying engineers of what needs to be done, but it is then capturing how that issue or that breakdown was resolved. And it's that sharing of information that feeds the learning aspect of this machine learning model, which is the brains behind predictive maintenance. So at some point, we will be presented with the question and the request of sharing information that our boats are generating. And it has got stigma to it, the idea of sharing information, and we are in a very confidentiality focused industry, but there is information being generated in the engine room that is non-sensitive, and sharing that will only mean that the solution itself is improved and gets better. A quick AI rendering of what future maintenance dashboards may look like, and it's not too dissimilar to what you may see on a monitoring system on board a yacht now, but it's got a lot more logic behind it. So forgive the crude AI ChatGPT version of this, but the information it's presenting is the same. It'll be presenting data in real time. It'll be identifying issues and then presenting users with troubleshooting guides. And an important part of this would be the human in the loop. And if you're looking into AI, very much get on board the idea of a human in the loop, because as powerful as AI is and as enormous as the potential is, having a qualified engineer or maintenance person over the top deciding what gets done and what doesn't get done is going to be critical to the success of these models. We recently had a graduate from a UK maritime college reach out and ask the question, what skills will they need to have to work on the most sophisticated, technologically advanced super yachts in the next 5 or 6 years? And we responded without hesitation. You need to be a wizard in the electronics field. You need to understand electronics at a high level. But you also need to look at vessels as systems. You need to be a systems engineer. And you need to understand that systems overlap and they interact, and where they interact, there's really important data to be captured. So if we can get on board the idea of sharing the information that our yachts and our vessels are generating, then this movement towards a predictive maintenance landscape is only going to be more effective.
We are ready for the questions from the audience. So if anyone wants to direct a question to the panelists.
Are there any moving parts in those reactors? So how do you turn it on and off? And just in case a boat crashes somewhere, can you make an emergency stop?
So the systems are designed that if there's a reduction in cooling flow in the store, so we go 100% zero.
Does it all the time run on 100%?
No, so the system will fluctuate, and you can control the index control on the platform, and it loads profits. So it doesn't take the load increases on the boat, it will ramp up, and when the load decreases, it will decrease. And that's one of the reasons that battery to balance out. This will help balance it all out. All the new systems will have to shut down in 200%. All of it. It's just the way they have to be designed now with the SMRs and the MMRs, so that our system will do that. Will do the same. Just as part of the same criteria.
And where do you go after 15 years to replace it? Any shipyard?
Well, obviously, this is all the public perception that Echo talked about earlier. We need the public to realise to be safe, and we want places like Monaco to pull in, which means that hopefully go to engine 92, dry dock somewhere, and just pop up all on the side of the boat. We're talking 15 to 20 years from now. To have a sort of time boat to continue to be on, but it's safe. And obviously, before that, we want the ability to sail into Monaco and Santa Fe and Caribbean as well. But we see that as the biggest challenge now, not regulation. Regulation is taken care of by LR and the other states. I know that will happen. That will come. This takes time to go. I know that the biggest problem we have is so hence the starting now. The reality is we want to build something. Designing, it's always designing, it's designing a boat for 103 meters, but it's one build that should be designing this system now. Whether you're designing it with nuclear in it, or whether you're designing it with electric. But when you put nuclear in, it's one build type. 2030 is a large build type.
If I may add a little bit to your question, Derek, just explain to us, you have 4 units. How, when you captain throttles the ship, what's going on? The unit is always producing, the power unit is provides more power. How it works?
For our unit, I think it's the same, but basically, if you welded out into a steel box, you would have 4 pipes going through the wall to the turbine. That's a cooling water in, out, here in tank. That's a 4 pipe. You just connect the landers, pull the unit out, put a new one in, connect it to the landers, off you go. The power generation section doesn't get changed in the reactor. That's been serviced all the time.
When you change the units, can you ship, after 8, 10 years, can you ship the unit to the place where the boat is and change in place, or you have to move the boat?
A couple of units on the dock, those will come out, those will go in, that'll go on the ship straight back to Houston, where it will be serviced, emptied out,
Fantastic. Any other questions? At what size, vessel size, does become cost effective?
We believe going from 40 meters up. Let's say your unit costs you, and I'm not going to quote me on this, but at the moment, $9.5 million. Right? You go, oh, that's a lot. But actually, when you look at the cost from a shipyard point of view of all the steel for fuel tanks, the exhaust system, the scrubbers, the 2 engines, the 3 generators to build the plane, the ventilation ducts, and then the maintenance and fuel that will put into those 5 diesel units over the next 3 to 4 years, and you will gain that cost back. And then after that 4 years roughly, then obviously everything else, that's still your profit. The cool thing is we don't have it here, I didn't bring it sadly, is we have an AI little video that shows a yacht in the future pulling into a bay in an island somewhere, plugging in, instead of taking power, we're powering the shipyard, we're powering the port, and all the lights go on and put it around the boat. So you'll be able to sell your power. Okay? That's the way we see the future. So we'll start talking to not only vessels as well, but also people who are doing power back. Give it and charge us 40 cents kilowatt. We're going to give it to you. Don't worry.
Helps pay the bills. For C-Hub, how can an incoming engineer crew learn a system mindset?
An engineering systems mindset. The best way to learn how to be a good systems engineer would be to structure the maintenance plan that you're in charge of in a way that allows you to learn how systems interact and to understand the relationships and how specific components impact other parts of the vessel. So gone are the days of simply providing a pop-up that a pump needs a rebuild. You want to build around that work an understanding of sea strainer locations, how that pump operates, the conditions that it should operate in, and how the whole system is affected by the breakdown of one part of that entire system.
You say 1 megawatt electrical and 2 megawatts heat. How can you more efficiently capture the heat energy? Is steam coming back?
We think one of these units, our power plant, like 2,000 a day.
Is the helium used for what? For cooling?
I was just curious, just as a non-technical person, is there any risk of exposure? Like, what if the boat catches on fire? Or, you know,
Collision?
drops the boat and the thing falls out.
You're probably going to lose your cooling pumps and stuff. When it shuts down to zero, that means there's zero output. No use there. The active output. And so it sinks. It will sit there in the shielding that it has, the bottom of the ocean, until we can get it out. It's intrinsically safe. And then it comes back to the upside. When you're designing one of these boats, you should be looking at backup for cooling pumps. If you get a blockage of the switches or an impeller going on a pump or vibration in the shaft of the pump and you start to reduce the flow, you want to be able to switch to the next pump or maybe another switches or whatever. So that's something that you need to have to design at the time. You want to make sure there's backup for all those systems.
If I may,
Can I just ask, so with other alternative fuels, one of the big issues is training the seafarers to deal with it. Can you explain the differences in, or is there any anticipated change in the training of engineers, for example, to handle these systems?
before I answer that, if I could just going back to Aaron's question, that's what the underwriters are asking as well. So they're asking what happens in a collision that has nothing to do with your reactor or some other purpose that the ship goes on fire or goes to the bottom of the water. So that's the question. And it's a similar question that you would ask whether it was a diesel engine in there or hydrogen package in there. You have to solve for all of those things. So the same salvage activity would take place, whether it's nuclear or non-nuclear, in the sense of the position and the condition of the ship. How they deal with the reactor would be different than the hydrogen or LNG or something else. So the salvage people are working on that, and they're creating operation plans so that the underwriters can look at it and say this is insurable. Just another comment on the cost, and I think Espen's done a great study, and Derek, our study, we've got two projects, one 120 meters and one 130. And when you get crossing over 90 to 100 meters, the percentage of cost is getting so low to the total cost of the ship. The same factors take place on the 40 meter that Derek was explaining, is the payback. But when it becomes such a low percentage of the cost of the ship, it becomes more adaptable for somebody to invest in it in the first instance. On the, was it the training? Southgate always likes to talk about training, and he should. I think, we agree. We've talked about this, Pete, and the STCW aspect has to be trained. What exists now? KW will make has an important, maybe secondary level of your STCW license, and then the particular aspects of when it's software driven and the laptop and what are the backups and so forth. I think there might be kind of a manufacturer's extra training that would take place, but I think the STCW is going to kind of find its way stay STCW, and then go with ship tonnage and TW.
EJ, going a little bit back to the legal side of this. You go to a dentist, you go to an MRI, and the operator goes behind a door and isolated, and we know that's human low radiation. Is there any legal liability related with people working around this nuclear reactor, even if it's small radiation?
Well, it's interesting because they have now an exposure factor for working around reactors now. So there's a percentage of radiation, percentage of time that you can spend in any duty period of the human. So those are being recalculated for the new technology. So once maybe you've seen some, Derek, some of those calculations.
You mean UV radiation? So it's basically safe, that you're saying. crew can enlist. Is the crew in charge of the engine rooms hired by the owner, or is necessarily supplied by the engine manufacturer? And as a battery, there is always a positive side.
Question, if you can clarify, Derek. I've heard you make reference to your system and Espen's system. You're collaborating together. Are they two different systems? They're going to be two different end products?
nuclear into the industry and clean it up, with all the gases and the toxins and everything else. And like I said, with ours, and it will still be the same with one that you can use them on land, but it just has to be at sea, especially for island groups. And we're I'm talking to a few island nations at the moment. It's a huge benefit, especially if you go to the Caribbean. They're always burning dirty food. Open up the atmosphere, and if they can't get the fuel from wherever they get it, from America or Venezuela or wherever, then it's food. Okay? And you know, and costs them a lot of money. So you buy one of these, and all of a sudden they become fully independent, and they control what's going on. Island fruit, totally.
Okay, any other? Oh, there is more. Please.
Does this shift the design challenges downstream? So if you have to have an emergency generator, your seawater systems, things like that, and you're looking up and downstream of the main propulsion system. Yeah, that's been might make most sense.
Can you repeat the questions, please?
Yeah, looking at the designing of the vessel overall,
Yeah.
upstream and downstream of the main propulsion system, obviously you're losing your ventilation stacks. You know, do you still have to have emergency generators on board that are diesel powered, or what other elements come into play when you change these propulsion systems?
Well, as I said, this is essentially just a diesel electric setup, except you replace the energy production system, the diesel generator, with a nuclear system. So you have thrusters, you have secondary systems, a battery package, probably your emergency power, but everything else pretty much remains the same. I just want to pick up on what you said here regarding, I think that in the broader picture, what's going to drive this nuclear power and small modular reactors is, one of the aspects is energy independence. When we see today with what's going on in the world and fuel prices, fossil fuel prices. And the other thing is, which is going to drive it, I think, is AI and the incredible demand for electricity to drive the data centers. And many of the big actors in the IT fields are now looking into sponsoring and investing in this because they know that they have to produce their own energy. So I think the public perception will be shaped by that as well. And I think that it'll be like an AI wave. It'll come very quickly and just accept it. That's my view on it anyway.
Just like to add to the answer on the redundancy is that what we're looking at on our projects is having a reactor separate. So we don't have the diesel backup. We have a reactor backup. So we have if the combination of the single, we'd have a megawatt or 2 megawatt, which is potentially also to be used as a get home, not just for emergency power, but to turn the propellers at a slow rate. And so we're looking at two spaces, one for the main plants, reactor plants, and then a backup plant that can come in as like an emergency generator.
We have approval and verbal principle of stories. Zero. That's a very we believe that with we're looking also at crafting factories to provide so the combination of the two means that you don't have to where it's 22 it's not free. It's in the side of our paper. Yeah, but you know, we're looking at that. We're looking at putting the grafting back. Now we're talking about the guys and get rid of lithium and
If you can power the village, the port, the marina, you can power the tenant for sure. I want to mention something that was mentioned before by Aspen, that talking with a client we are working about, he was very receptive to the idea of nuclear propulsion and very attracted to the idea to be able to go out for 10 years, just for security purpose. Just with the family. And they talk about large boats, the one that, not just your house that you take with you, like a fly breeze or something, but large boats that you take the village with you, you take the movie theater, you take everything, marina with you, etc., etc. So you can take your family and a lot of guests and be independent for 10 years. There's a lot of people in being communication. That's attractive to a lot of people today. So I think that's one of the, probably the first buyers. I don't know. I'm just thinking about that. Any other questions? Okay.
One's for Espen. Espen, when I discussed this with colleagues, Jonas at Monaco Yacht Show, I was asking about the fuel and the low enrichment level, like it's a 5% or something like that. He smiled and told me to put my hand out, and he put in my palm of my hand one of the fuel pellets, without any worry of radiation or anything else. So maybe you could comment on that.
I said it's encapsulated carbon, and it's not something you can easily travel with, so I didn't bring it here. It's hard enough getting into the States these days without that. But absolutely, it's a big part of the whole thing that this fuel is intrinsically safe, and that's one of the real revolutionary aspects of it.